20 centimeter long section of copper pipe has a 1 centimeter thick wall and outer diameter of 6 centimeters.
Well, a
20 centimeter long section.
okay, hold on. 20 centimeter long section.
1 centimeter thick wall.
Okay, hold on. So now we've got, this is a cylinder, right? You got 1 cm thick. Okay.
And then outer diameter of 6 centimeters.
Six?
Outer diameter of 6 centimeters.
Alright. So 6 cm, go ahead.
And then it just wants you to, it's like a 3-part thing. It says sketch the pipe.
Alright, this is sort of a sketch of the pipe. It should be, if this is the z-axis, it should have a height of 20 centimeters. The outer diameter is 6 centimeters. That means the inner diameter is not 5, but it's going to be, if you think about that, since it's 1 centimeter thick, it would be 1 less here, 1 less here, it would be 4 centimeters. Y'all with me? This would be 4 centimeters. And this is the thickness. This is the pipe itself I'm trying to show you. Just sort of a sketch. Go ahead.
And then the second part is determine the total surface area.
Surface area. All right, this is one of those things can be a little tricky. I want you to just understand something. When we're talking about surface area of things like spheres or cylinders, it's important. If you have a cylinder, just a cylinder, all right, of a height h and a radius a, well, what common sense says, if you just would cut this at any point straight down and peel it, you would have a square piece like this. Does that make sense? Of height h. Y'all follow me? Now, this length would be the actual circumference, which is 2 pi a. This would be the height h. That means the area here of that, the surface area of a cylinder, would be equal to height, which is h, times the circumference, which is 2 pi a, or the perimeter. Called perimeter back in the day. Either one. Y'all with me? Now, when you talk about the surface area of this cylinder, I want you to just appreciate what he's trying to get you to do. Focus and not just casually move through. There's an outer surface, right? Y'all with me? Then there's an inner surface of that cylinder. And then there's the top surface and bottom surface. Y'all with me? So we're going to talk about each of those because this causes you to focus on what's going on. Y'all agree that the cylinder itself, the curved cylinder would have height times 2 pi the radius. Do y'all agree with that? Now what about this top and bottom? Well, when we talk about any type, this is the way I like to do it. I mean, that we could write an integral for this, but it doesn't really benefit your insight. If you have anything with the radius, inner radius A, outer radius B, and you're talking about this area here, the way I recommend you think about a problem like this is think about what you know that has that kind of concentric shape or a conical shape. You all know that you basically have a circle there, don't you? A circle has an area of pi a squared, doesn't it, class? So when we talk about the shaded area here, well, we could say it would be the area of the outer circle, pi b squared. You all agree that would be the area of this outer circle, correct, class? And if we subtract from it the area of the inner circle, right here, then the remainder would be that cross-sections of area. Do you agree with that? So then you can come up with a basic formula. This is really what? Just pi, and it's times outer radius squared minus inner radius squared is the area of this shape. Now when we talk about this cylinder, I'll do it right here. I'm going to go ahead, first I'm going to take the area of the outer cylinder surface, all right? So that would be a height, and then it would be times 2 pi, and the actual radius would be 6 centimeters, or it would be 6 times 10 to the minus 2 here, right? That would be the area of this outer cylindrical surface. Do you agree with that? I'll just leave it as h. Can everybody follow me on this, class? Now I'm going to add to it the area of this inner cylindrical surface, right? it's still gonna have a height h, and I know h is 20 centimeters. I'm just writing this down for now. Y'all with me? So the height is the same, but then it would be 2 pi 1. Well, the inner radius would be 4 divided by 2, or 2 centimeters. Do y'all agree with that, class? So that's going to be times, I'm sorry, I put 6. This should be 3. I wish somebody, this is 2 pi a. If the diameter is 6, the radius is 3. You follow me, class? I'm sorry, I made that mistake. You're asking about this. Do you understand what I'm doing? 2 pi, and this is going to be times 2. This, I'm sorry, I said that, and I didn't type it. It should be 2 times 10 to the minus 2 here. All right, so that, and this h, of course, is 20 centimeters. Now I have to get the top and the bottom. Do you all agree that this cross-hatched part here, the top of that, would have the same surface area as the bottom? Right? So I'm just going to put plus 2 times, and that would be pi, right? And then it's going to be the outer outer radius, which is going to be 3 times 10 to the minus 2 squared minus 2 times 10 to the minus 2 squared. And that right there, this should be the area. Do y'all agree with me? All right. And can you tell me what it is? H is 20 centimeters. We could make this, we could bring a lot of stuff together here, so I can say, since H is 20 centimeters, the area would be equal to 0.2, and then there's a 2 pi, and then it's going to be 3 times 10 to the minus 2 plus 2 times 10 to the minus 2, or really this is going to be equal to 5 times 10 to the minus 2. That's the area from the top part there. Here, it's going to be added to that 2 pi, and then there's going to be 10 to the minus 2 squared is 10 to the minus 4, and 9 minus 4. So whatever that is, that's the area. Can you give that to me, anyone? I'm just adding up the parts of it. Can anybody give me that? I suppose I could factor the 2 pi out in front too, but just run the numbers on that and give it to me. You don't mind.
Yeah. Yeah, I got it.
What'd you get?
You get 0.065.
0.065 meters squared. Anybody else get that? That's the only thing you're doing is adding up the sections. What did the book say? The solutions. Nothing?
It's an even number.
Oh, well, didn't I put the solutions up? Which I
Yeah,
did.
you got it.
Can you tell me if that's consistent with Whitmer's?
Looks like he got 660 centimeters squared.
Well, the .065, there's some rounding.
Yeah, yeah, 166. Yeah, he rounded, his rounded up to 0.66.
All right, don't worry, we're right. We got it. What's the next part?
Next part was determine the weight of the pipe, given the density of copper. And the
Alright.
density is 8.96.
Okay, we'll get to the density in a second. If you want weight, you really want volume, don't you? Y'all follow me, class? You don't want surface area, you want volume. Volume times density will give you weight. Density is going to be so much mass per centimeter cube or per meter cube. So we got to find the volume. How do you find the volume of this kind of a pipe right there? People? I'll take it.
Subtract the volume of the inner one from the volume of the.
No, you can't subtract. Okay, now I take it back. If you were thinking making this a certain thickness or a certain height, yes, what he said is this, and you're right. He said, assume the pipe is 20 centimeters long, and you have a pipe, solid pipe with radius B. So the surface area would be pi b squared, right, times h. He's absolutely right about this. Then if you subtracted the volume, or I should say not surface, the volume of the inner one, you would have it. You're absolutely right. So here, what I'm gonna do is this. Now we could write a volumetric integral and do it, but the reason I'm not doing that, I prefer you to do this in a way that is most meaningful in the long run. You should recognize certain geometries, cylinders, spheres, and know the volume of both very well, and the surface area. So when you talk about volume of a cylinder, volume, and this is going to be just for the cylinder we have the volume. I know it's going to be the surface area of the actual cylindrical top, which is going to be pi a squared. This is just putting a general formula down, times height. That's volume for any cylinder. Do you all agree with that? Radius squared times pi is really the surface area of the circle times the height would be the volume. Now when we take volume of that cylinder, like he said, we're going to take pi times h, and h here would be 20 centimeters. Then we're going to take the outer radius, which is 3 centimeters, and we're going to square it. And then we're going to subtract the radius of the inner one, which is going to be 2 times 10 to the minus 2 squared. And that will give me the volume, right? So that really, well, what is that? The volume is going to be pi times 20 centimeters, 0.2, and then it's going to be 9 minus 4 times 10 to the minus 4th, and that would be the volume, whatever that is, but it doesn't matter what it is at this point. We can get that number. Now, to get you want the mass? Is that what was that?
What's the density? No, it's the weight, yeah, the weight.
Weight or mass? They're different. All right, weight is going to be, well, what does he give you? Does he give density in terms of?
It's grams per centimeter cubed.
That's not, mass is what he's talking about. Mass is in grams, so he didn't, weight would be the actual, something you put on a scale and measure, so that would be in pounds or newtons or something like that. All right, so he gave you a density of what?
8.96 grams per centimeter cubed.
Grams per centimeter cube? All right, I'm going to change this to grams per meter cube because our volume is going to be in meter cube. So if we're going to do this, you think about this, we've got centimeter cube we got to get rid of, right? So how do we go about doing that? Well, we know that there are 100 centimeters in a meter, right? So we have 100 cm per meter, and since that's cubed, this has to be cubed, doesn't it, class? So it's going to be a factor of, that's 10 squared to the third is 10 to the 6th times this, or the actual density per meter cube would be 8.96 grams per meter cube. And now times 10 to the 6th, pardon me, times 10 to the 6th. 8.96 times 10 to the 6th grams per meter cube, and you'd multiply it by this volume, whatever it is. What is this volume anyway? So I got 5 and times 0.2, it's going to be 1, which is nice, so it's pi times, so it's really, this is pi times 10 to the minus 4, right? That's going to be the volume in meter cubed. And that means the actual value of the weight or the mass, total mass, is going to be 8.96. This is the density right here. Maybe I should put it down. It's going to be the density times the volume. and that density is 8.96 times 10 to the 6th times pi times 10 to the minus 4. So can you just tell me that? And this would be in grams, by the way.
2,814 grams.
2,814 grams, or 2.814 kilograms, right? Correct, class? All right, that was the problem. Go ahead, was there another part to this?
That's it.
This is really just getting familiar with the shapes and how to get volumes and surface areas. That's the only thing. The density is just through that. Okay. Now I'll say one other thing. If it was a charge density that was constant, then we just multiply the charge density by the volume to find the total charge. And that's it. Other questions about the homework? Okay. I wanted to pick up on spherical coordinates because that was the last part that I really didn't get into. I want to make sure you're clear on this. Did you all see that handout I put up there about the different coordinate systems and their volumes and surface areas and unit vectors and all that stuff, class? Did you all see it? Wasn't that posted up there? Right? It should be very informative because it collapses everything down to a couple of pages instead of reading through 5 or 6 pages in the book. And it really does a good job. So anyway, we did cylindrical, right? We did Cartesian. Now, to finish up spherical coordinates, the whole deal is, well, if you look in your book, it's probably better for you than my drawing, but I'm trying to show you an X, Y, Z coordinate system, and then superimposed on that is going to be my spherical coordinate system. So with spherical coordinates, you always start with a radius vector. If you're talking about, and this has to do with labeling points first and foremost. So if you have some point out here in space, it could be defined in terms of an X, Y, and Z. Do we all agree with that? It could also be defined in terms of a rho, phi, and Z. That would be cylindrical. And in terms of a spherical coordinate. All right? In spherical coordinates, you go from the origin to the point of observation. And actually, that's a straight line. It's a radius vector R, right there. And in terms of Cartesian, R is just equal to the square root of x squared plus y squared plus z squared. So it's really just the distance from the origin to the actual point. And I'll call this just P1 right here. Then the next coordinate you have is something called theta, and that's measured here. Theta is always measured from the z-axis to the radius vector r. And I don't like small r, I like capital R for radius vector. He uses small r in the book, I use them interchangeably. I'm gonna just do that. And the way you order points in spherical coordinates, in Cartesian it's x, y, z. In cylindrical it's rho, phi, z. And in spherical it's gonna be r. I'm using capital R. In his book he'll use small r, but my small r's are hard to distinguish them. R, and then it's theta, and then phi. Now, when you take a look at phi, what you have to understand is if you would shine light straight down the z-axis, and this was a solid line from the origin to this point, it would cast the shadow in the xy plane. That shadow is rho. You with me on this, class? Can you all imagine? And the distance from the x-axis to rho in the plane, the xy plane, this is phi, right there. And if you want, I think they show you all the relationships, but if you think about this, since I would know R, if I wanted this angle, just think about the ways you could get it. There's several. If I wanted this angle right here, right? Just look at it. By looking, you can see that really this distance here, I have it coming from here out to this point, but more appropriate would be like this. This distance right here, but I'm trying to show you that it's just the Z distance here. That's Z, right? And that's R, and this is an angle. Now just think about this. Adjacent over hypotenuse is cosine of theta, right? Do y'all agree with that? That's one way to get it. Another way to get it, now think about this. Opposite over adjacent is tangent, right? So the tangent of theta would be opposite, which would be rho over Z. Y'all follow me on this, class? And in the book, I mean on the actual notes that I posted on there, they show you several different ways of defining theta, R, and phi in terms of X, Y, and Z, or in terms of rho and phi and Z. Okay, so there's different transforms, and try to become fairly familiar with that because you use them all the time. Now, when I do this, the next thing I want to do is talk about the differential volume and differential length. So, for spherical coordinates, when I take a look at differential length, remember you got unit vectors. I didn't actually show you here, but you're going to have a unit vector in the radial direction. That would be AR. Then you're going to have a unit vector in the theta direction, since theta is measured this way, and it would be like this. This would be A theta. And then you're going to have a unit vector in the phi direction. That is going to be pointing into the board and would be A phi. You all follow me on that? There are 3 unit vectors, and at a given point, they're all orthogonal. AR points in the direction of the radius vector, but it has a unit length. A theta would point in the direction that the tip would move if you would freeze R and just increase or decrease the angle theta. So it's this direction, like the tip of a windshield wiper. And we talk about A phi, well, that's going to be in the XY plane, and it's the projection of this here. If you would just wiggle this right here in the phi direction, the tip would move that way. That would be A phi. So the differential length, you start off with just dr AR, right? And you can use small or large r. Then the next one you get is going to be R, that's the radius vector, times d theta, A theta. And that's, the reason that R d theta there is because now you're taking a look at the differential length associated with the movement of this tip. And the movement of that tip, the distance, is proportional to R. You all follow me on that? Longer R, the bigger this is. Then you're going to get this. You're going to get R, and then it's going to be the sine of theta. And what this is taking this radius vector R, and it's taking the projection of that in this plane. So it's really talking about this length here. And it's going to take R sine theta, since that's theta, it would be this distance, it would be opposite over adjacent. Then when we wiggle it with respect to phi, that's the differential there. These take a little time to get used to, and you're going to have to do some problems. Y'all with me on this? At least understand what they mean to do. They're showing you a differential length and the actual spherical coordinate system. When we take a look at volume, differential volume, and I can do it this way, it's usually just dV. The only thing a differential volume is, I'm not going to attempt to draw the cube again, but you know what I'm talking about when I say that there's going to be a differential cubic volume here that just is composed of differential lengths in each direction. Can you all imagine that? And there's a good illustration of that in the thing I provided. Well, it is just ignoring the unit vectors and multiplying the actual scalars in front of it. That is the differential volume. So it's going to be, if you look at this, you got R twice, so it's going to be R squared, and then you're going to have a sine theta, And then you're gonna have dr, d theta, and d phi. And that is the differential unit of volume in spherical coordinates, always. Now, differential surfaces are a little different because remember, there's 6 surfaces in a cube, right? And that means if you want the differential surface, and I'll just do one of these, but you can look. Suppose, maybe I'll do 2. Suppose I wanted the differential surface associated with this outer portion here, right here. Can y'all imagine that? All right. It'll always have a direction. In this case, it would be the AR direction. Just, take R and just shoot right through there. Y'all follow me how it's normal to that surface? So if I was talking about this differential surface right here, then it would be equal to AR. That's the direction. Now, the minute I see that, I know that the 2 other differentials will not have dr in it. They'll have a d theta and a d phi. Do y'all follow me on that, class? They can be a function of R, but not dr. It will not have that differential. So when I look at this, the one that goes this way is that arc length, like I say, the tip of a windshield wiper, and that's going to be simply r d theta. Y'all follow me on that? And then there's the one that goes this way, and think of that horizontal projection of r vector. So the horizontal projection is r sine theta, right, in the plane, and then the wiggle is going to be d phi. Now that would be the differential section of this outer differential surface there. If you went right through that little differential cube to the other side, what would change? Differential surface behind it, directly behind it. Class? Yes, the direction would be minus AR. Do y'all follow me? Remember, differential surface always points outward from the any closed surface. All right, if I'm going to just ask you this, and this is a tough one. What if I asked for the differential surface associated with this side? Try to imagine that. All right, first, which way is it pointing? It's coming either out of the board, right, or into the board. What direction is that?
Out.
Say again?
Out.
Well, I mean,
Oh,
A phi, right? It's going to be a minus A phi because it's pointing this way, right? If it was pointing that way, and this is terrible for me to illustrate, but it would be a positive, it'd be minus. Do y'all follow me? It's in the A phi direction. Give me that one. All right? Now that means the differential associated with this can't have a d phi in it. Y'all with me? So this is going to have this side here. What is that differential, class? RD theta, right? RD theta. And then what about this one going straight radially outward? DR, isn't it? So it's RD theta DR. Read that. How many understand that? You may not want to participate in this little thing because it looks a little nuts, but try to understand. I'm trying to just give you insight into how you find a differential surface. First, you find out every surface is planar when we talk about differential surface. Find out the unit vector that pierces it normally. So that's the direction of the surface. Now, once you got that direction, the differential surface will not have a D, whatever this is. If it's an R, it will not have a DR. If it's phi, it will not have a D phi in it. Now, whatever is left, those are going to be the differentials that are associated with that surface. Sometimes there's an RD theta, and sometimes it's R sine theta D phi, but you have to be careful about it. Fair enough? I'll give you some more of this, and as we work problems, it'll become apparent to you. All right. So that's the differential surfaces, differential volumes, differential length. Now the next thing we do, and I expect you to kind of appreciate this because you've had physics, and at least from a physics standpoint, if you have something related to a point source, like we know, I put this up here earlier, but we know if you have not last lecture before that, if we have a charge Q and we're a distance R away from that there is an electric field, and this is right out of your physics books too, that's equal to Q over 4 pi epsilon naught R squared, right? And then it's in the AR direction. Do y'all remember that? That was the electric field. We got that from the force equation, right? By dividing the force on charge 2 by charge 2, and we created something called the electric field. What are the units of the electric field anyway? Yeah, we use volts per meter. Do not use CGS units. And I think your physics course, if you had it here, was in MKS, right? It was volts per meter. Do y'all remember that? You had volts, right? Volts per meter. You did not have any British thing. I mean, it's crazy CGS units. I don't use them myself. I don't like BT. Did y'all have thermo yet? Oh, don't you have to take them?
Yes,
You take sort of a
eventually.
Well, thermo is one, to me, speaking from my experience with thermo, when you take mechanical engineering thermodynamics back in the day, it's a huge amount of steam cables and converting BTUs and all this stuff. So you're going from conversion factors from British thermal units to actually joules and stuff like this. And it drives me nuts. I don't like it. Anyway, it's a waste of time in my book. Don't sue me for this. Anyway, that's the electric field from a point charge. So if it is from a differential charge, if we have a charge dq, this should make perfect sense. We got a charge dq, we're going to get distance r away, and now we want the differential electric field. That's simply equal to dq over 4 pi r squared epsilon naught, or 4 pi epsilon naught, in the AR direction. Do y'all agree with that? You go from a point to a source, to electric field, that's a singular charge, to a differential amount of charge gives you that differential electric field. Now, and this is what I call the building block approach. Well, what if you have a whole bunch of differential charges and you want the electric field from them? Then you would say the electric field from a bunch or a distribution of electric charges would be equal to the integral of, in this case, I put dq down here, but dq, if it's volumetric, would be the volume charge density right here times the actual differential volume. So you would simply have the volume charge density of the, whatever that is, charge density, times the differential volume over 4 pi epsilon naught r squared, and it would be in the AR direction. This would be over the volume. Now that's if it's volumetric, and it should make sense because you've done stuff like this many times when you had physics and in your other coursework. If it's not a volumetric, if it's a surface, then this could also be something where you had the integral over the surface of rho s, that's the surface charge density, over 4 pi epsilon naught r squared in the AR direction, and it would be over the surface. And finally, if it was a line charge density, it would be rho L, that would be a line charge density, AR dl over 4 pi epsilon naught r squared. And here, this would be over the length of the line. All three are just taking a differential charge, finding differential field from a differential amount of charge, and then integrating it over the surface where the charge exists to get the total electric field. And the best way to see this is demonstrated with an example. Probably there's two examples that come to mind: infinitely long lines and just circles. Like I take wire and make it a loop and go right up the z-axis. Okay, I'm going to do the wire up the z-axis. No, I'm going to do the loop first. I like this one for a reason, because there's a lot of insight you get in the way to do these for this problem. So this is going to be a simple line wrapped around. It's going to be a wire, circular wire. This is going to be the z-axis. And what I'm going to do is I'm going to take a wire or a circle, and I'm going to symmetrically lay it in the XY plane here. So it's going to be like this. That's supposed to be a circle of radius A. Y'all with me? And this is in your book, and this is going to have a charge density rho L. That will be the charge density on this. Y'all with me? Can you all imagine that, class? Can somebody give me a page number for when this is in your book? It is in your book. It's a classic example. When you had physics, your professor probably did this one too.
144. Is that row out?
Yeah, it's rho L. It's a line charge density. All right, so here's how we go about doing this. First, I'm going to say there's a differential amount of charge here. I'm just going to call it dq. And if I want the electric field up and down the z-axis, so I'm going to come up a height z, and I'm going to draw a radius vector from this differential amount of charge here to this point, r. And then I'm going to get a differential electric field right there. That should make sense to you, at least my intent. With me? Okay. Now this problem lends itself to cylindrical coordinates. It's obvious there's a cylinder basis for this, right? So here's what we'll do. We'll take dq, and we know dq is really the amount of charge is the charge density, line charge density, times dl, right? That should make sense, correct? Now what is dl is the next thing. Well, here I've got this length here, differential length. It's at a constant radial distance a. Do you agree with that? Well, that differential length would be a times d phi. You all see that? The differential length for this one would be a. That would be the radius of my loop times d phi. How many see that? That's like the typical wiper, right? A radius a, if it moves, it wiggles d phi, right? Then the tip moves a d phi. So that's the differential length. Meaning my differential charge is actually equal to rho L times a here, the radius, times d phi. That's fine. Now I need r. So what's r equal to? Try to appreciate my drawing. This has a radius a and a height c. I want the electric field right here. I want the electric field on the z-axis at a height z away from the center. With me? So what is this distance r? Well, do you all agree it would be the square root of a squared plus z squared? How many see that? That's a right triangle, isn't it? Right there. Y'all with me?
Oh, yeah.
All right. So this r would be equal to the square root of a squared plus z squared. Okay? We're good so far. Now we need a unit vector in the direction of r. So now I need AR. And I come back here. So really to get a unit vector AR, I need vector R, right, over the magnitude of R. Do you all remember unit vectors? So how do we get this? Think about this logically. This, I mean, if R is pointing from this point to this point, this is the direction it points. Do you agree with me? So the way we get unit vectors is we take the points of observation and we subtract from them the points where the vector originated to get the vector length. Just watch me. So what's the R value on the z-axis, people? Your instincts are correct. It's 0, isn't it? Y'all see that? If you're on the z-axis, there's no radial distance difference, right? We're doing this in, I should say, row distance. Let me be clear about this. This is the radius vector. It's rho, not capital R, okay? So here when I get this R vector, first I take the difference in the radial components, which is going to be z minus a, because that's a constant radius, right? and this would be AR, or I should say A rho, pardon me. Then I'm going to take the difference in heights. Now, I want you to just follow me on this. The coordinate I landed at has a height of Z, correct? What is the coordinate down here? 0. So now it's going to be Z minus 0. A Z, and something that should trigger you, so what about a phi, right? Now here's a rule of thumb. If your coordinate axis is the place where you want the electric field on, a phi has no meaning. Just listen. A phi has absolutely no meaning on the z-axis at all. You can forget it. There's more to this that I can't tell you right now, but it makes no difference at all. This is your actual vector r is really equal to simply minus a rho plus z. This will be in Whitmore's book. Y'all follow me on that? Now, once you got that, you can get this right here, and that's simply equal to minus a rho plus z. Well, if that's vector r, then the magnitude of that is just the square root of the component squared. Do you agree with that? Right? So I would divide this by the square root of a squared plus z squared, and that would be a unit vector right here. They are. Now I'm going to assemble the electric field integral for this. And you'll see this. Remember, I want this on the z-axis, not off the z-axis. I want the electric field anywhere on the z-axis. Your instincts are going to tell you something about this in a second. And we're assuming that the charge density, or the line charge density, is a constant. When we take a look at the differential electric field, I know it's going to be the differential amount of charge, so that's rho L A times d phi. Then it's going to be divided by 4 pi epsilon naught. And then it's r squared. Well, r squared, if that's r squared is just a squared plus z squared. Do y'all agree with that? Now, I have to multiply by AR. So I do it right here. And AR is that. Now you'll notice this is divided by a squared plus e squared. Do y'all see that? Square root of that. You'll see you have a squared plus e squared here to the 1 power, or to the 2 over 2 power, if you think of it that way. It's going to be that times another 1 to the 1/2 power. So what I can do is just make this to the 3/2 power. Do y'all follow me on this, class? Because normally I just put a square root of a squared plus z squared down below that, but I can see I already got a squared plus z squared by itself, so just take that quantity and add another 1/2 to the superscript, or to the exponent. You got that, everyone? All right, that's the differential electric field. Now your gut would tell you that I have only a d phi integration coming up. You all see that? So I'm only integrating with respect to phi. But there's one thing that should bother some of you, this term. Remember how I said that a rho points in a different direction at a given value of a, or at phi, right? Now this, what I'm really trying to say is when you have an x coordinate, if you have an x, y, and z coordinate, ax is always that direction. Got me? It never changes. If that's true north, it's always true north. When you have an a rho, and it's pointing that way, but if you're at a point here, is this for a constant distance rho? As I move it, then a rho points that way, right at this point. You all with me? So it's not always pointing true north the way the x, y, z. So the way we get around this, Dr. Wentworth will say this: when I go ahead and get the total electric field, I do the integral of this from 0 to 2 pi. And that would give me the total electric field E, right here. This should make sense to you, because if that's the differential electric field from this piece right here, if I integrate all the way around there, it has to be from 0 to 2 pi radians. Do you agree with me, everyone? Now here's the thing, Dr. Wimper says this. He says, well, common sense will tell you, for this component caused by this one, if I go right through the origin, and he'll call it the conjugate point or something like this, there exists another DQ right here, same magnitude, that would cause the same exact kind of electric field, differential electric field from it, to sprout up there. Do y'all follow me? And one thing you'll notice is the horizontal components annihilate each other. That's his argument. Do y'all follow me on that, class? Only the vertical components will add together or be in the same direction. The real truth is, and I want you to appreciate this, if you take a look at a row in terms of x and y unit vectors, that's equal to cosine of phi ax plus the sine of phi ay. You're going to have to just take my word on that. But at any given value of phi, that's the unit vector a row in terms of an x and y. And you'll see if phi is 0, if you're on the x-axis, then the unit vector, if cosine of 0 is 1, it's all ax. You all see the sine of 0 is 0. Correct, class? And this is something that's absolutely true and has absolute coherence, and there's no problem. If you put this value for a phi in and then do the integrations, you're going to be integrating a cosine or a sine, d phi, from 0 to 2 pi. What is the one thing you notice about sines and cosines with trigonometric integrals? Anytime you integrate a sine wave from 0 to 2 pi, what do you always get? 0, because the volume or area above is the same as the area below the actual 0, or you could say the 0 point. Integrated cosine from 0 to 2 pi, you get 0 as well. So when you replace that with this, with that, then it does annihilate the horizontal component. You're only left with a vertical component. Are you with me, class? Now, here's the real bottom line answer to this thing. When you do this, this component will go away, guaranteed. But look, here's the one thing I want you to see. When I do this integration, does A ever change? No. Does the point of observation we're looking at the electric field ever change? No. What's the only thing that changes? The phi goes to phi in the integration. That means all that other stuff is a constant. So you can say that the E field on the z-axis is equal to all this stuff, rho L over 2 pi epsilon naught, and then you can put A there, right? And then you can put A squared plus Z squared here to the 3/2 power, and then you can put Z here, and then when you integrate the phi, you get simply 2 pi. So the thing that's observed here is 2 pi into 4 pi is 1/2. You all see that? And that means when you're done at the end of the day, this is the electric field on the z-axis. If you've got a symmetric charge distribution, symmetric line charge at a circuit or at a distance a, forming a circle around there for a loop. That's the electric field above and below. There's one thing you have to see here. What happens when Z is negative to this value of electric field? Changes direction. It becomes negative, right? Now this should make sense. Think of this. If these are positive charges, right, on that loop, the electric field always points away from a positive charge. Do you all agree with that? So if I'm above the z-axis, it's got to be pointing up on the z direction, right? And if you're below the z-axis, it's got to be pointing down, and that checks with that formula. You all see that? Take a look. Because Z's in the formula, right? And this would be the electric field, and this should have an AZ. I didn't put it in here. There is an AZ here, but it would be in the z-axis. I'll give you some homework on this stuff. I didn't get to the infinite line charge. I want to spend a little time on that. Did you understand this lecture, people? All right, please do the problems. It's essential.